Let's try another example of a system that's at static equilibrium. So in this case, we have a sign hanging from a rod that's attached to the wall with screws, and then also there is a cable holding it up, which is attached to the rod. So we have the mass of the sign, the mass of the rod, the length of the rod, the length of the cable, and the angle at which the cable is attached to the rod. And we want to know what is the force exerted by the screws on the rod, and what is the magnitude of the tension force in the cable. Okay, so again, there's a lot of information to digest here. The important thing is to be able to read that problem, identify that this is a static equilibrium question, and then follow the procedure for a static equilibrium question. So first off, you start with free body diagram. So we need to start analyzing what are the different forces to include here. So we want a free body diagram of the rod / sign part of the system. So we are going to have here the mass, the weight of the sign itself. So that's going to be, I'm just going to ignore units for this just to make this a little bit easier to write. So then that'll be 5G. And then we have the mass of the rod. So that's going to be a force acting in the center of the rod. And that's going to be 2.5G. We've got the tension in the cable. So that goes in the direction of the cable, but has an unknown magnitude, T. And then lastly, we have the force exerted by the screws on the rod. That force acts at the point where the rod is connected to the wall. We don't know anything about the magnitude or direction of that force, but you can probably guess, if you think about it for a minute, that that force is probably up and right somehow. It's up because the screws are presumably part of what's holding this up. And it must be to the right because there are no forces pointing to the right. So something has to be a force to the right, or else this thing can't be at static equilibrium. So let's call that Fs, force of the screw. Okay, so there I've got 4 forces in my diagram. Now, we begin the actual problem solving kind of procedure. So if I want to approach this as a static equilibrium problem, the first thing I'm going to do is write down an F equals ma equation for this. So I'm going to have F equals ma equals 0 because the acceleration equals 0. And there's 4 forces acting on the system, but this is a 2-dimensional one. So I'm actually going to have 2 F equals ma equations, one for x direction, one for y direction. So in the x direction, I'm going to have the x component of the screw force in the positive direction minus the x component of the tension force, which is t cosine 30. And so that's going to equal 0. And then in the y direction, I'm going to have y component of the screw force plus y component of the tension force, which is t sine 30, minus 2.5G minus 5G equals 0. So that first equation is easy to simplify. Well, actually, maybe let's not get too carried away yet, because I've got in these equations, I've got 3 variables. Fsx is a variable, Fsy is a variable, and t is a variable. So I have 3 variables. I only have 2 equations. So I actually can't do much with this yet. I am going to need a 3rd equation so that I can have a system of 3 equations with 3 unknowns. That 3rd equation is going to come from my torque equation. So let's shift focus for a minute. Let's write tau equals 0. Now I need to choose an axis of rotation. I would like to put the axis of rotation here at the end of the rod there. The reason being, by placing the axis of rotation there, I can cause the screw force to exert no torque, and that's going to make my equation a lot easier to handle algebraically because it's going to eliminate two of the variables from this equation. So once I get rid of that guy, I am going to have 3 torques appearing here. The torque from the rod is going to be first of all, it's clockwise. Second of all, the force is 2.5 G and it is tangential. And then third of all, I need the distance from the axis to the 2.5 G force. That's going to be half the length of the rod, and the length of the rod is 2 meters, so half the length is going to be 1 meter. So it's going to be minus 2.5 G times 1. So minus 2.5 G. Now we've got torque from the sine. The sine is exerting clockwise torque, so that's minus. And the force is 5G. It is tangential. And now we need the distance from the axis to the sine. That's going to be the entire length of the rod, so 2. So this one's going to be minus 10G. Then lastly, I need the torque exerted by the tension force. Now this one, well, first of all, it's clockwise. Second of all, I do need to think about components here because this force is not tangential. I need only the tangential component. So that's going to be T sine of 30. And I've hit a little bit of a wrinkle here now because the distance between the axis and the force is not given in this case. But I do know that both the rod and the cable are 2 meters. So therefore, I should be able to figure out the distance from the tension force to the wall because I've got a little right triangle here. This is the distance I'm interested in. This is 2 meters here. And this is 30 degrees. So D should be 2 meters times cosine of 30. So that's the length of the cable times cosine 30. So that's going to be, let's see, 2 times sine of 30 is 1. So it's just going to be cosine of 30, which is 0.866 T. Okay, so there's my 3 torques. So if I sum those 3 torques, I should get 0. So I'm going to have 0.866 T minus 12.5 G equals 0. I can solve that right away. That one only has one variable. So the tension force is equal to 12.5 times 9.8 divided by 0.866. And that gives me a tension force of 141 newtons. So there's my tension force. Now I can go back to these other equations and plug in the tension force and solve these quite easily. So the x component of the screw force is going to be T times cosine 30. So 141 times cosine 30, which is 123. And FSY is T sine 30, sorry, is 7.5 G minus T sine of 30. So that's going to be 7.5 times 9.8 minus 141 times sine of 30. And I got, that can't be right. I think I punched it in wrong. minus 141. Really? 3 newtons? Okay, that's what I got. Yep. Okay. So there's the two components of the question was, what's the force exerted by the screws? That's here. It has components FSX is 123, FSY is 3. So that's the force exerted by the screws. And then second question, what's the magnitude of the tension? 141. So like, for example, if this was a real life problem, this kind of thing would tell you, like, what do you need to make the cable out of in order for it to be strong enough to hold up the sign? What do you need? What kind of screws do you need to use in order for them to be able to exert the force necessary to hold up the sign, and so on. And also, like you can see in this case, the screws are exerting quite a bit of horizontal force. So you have to make sure that you anchor this correctly into the wall so that they're able to exert the right forces and that type of stuff.